Okay, we're a little late in the recording process, so we go back. If this is my force, then this is work, which we sometimes write in this form, even though this is actually what we do. If this is my position vector, then this is the RDT. We know that. So therefore, if I want to do force dotted with dRdt, stare at what we have here. We would have m times dx dt plus n times dy dt plus p times dz dt. Okay, great. But this isn't work. This is what I have to integrate to get work. So I want to say work equals now remember, you're only going to see t's, aren't you? You're not going to see x, y, z. You're going to only see t's. Well, we know this from u substitution. Again, I'll remind you, when you're integrating du dx with respect to x, that's the same as saying I'm integrating with respect to u, because there's actually only that variable. If I'm doing dr dt integrated with respect to t, we often just write it this way. What would this then be? Does this look familiar? This is what we did yesterday, isn't it? And I said yesterday, when we did these integrals, these weird integrals that had dx's and dy's in the same integral, what the heck was that? I said, the force is in that integral somewhere, right? It's in there somewhere. You didn't know where it was, but I said it's in there and it's going to show its face today. This is the integrals we did yesterday. They looked like this. Can you now see where the force came from? Yeah. When I did f dotted with dr dt and integrated with respect to t, we used this notation. But what did we do? We changed everything to t's, ultimately. We actually did make everything a function of t in the end, so we could do one integration, not multiple things here. So the most common form of a work integral is something in this form right here. Whether this is three-dimensional, that's two-dimensional, same idea. Okay, I'm moving around a plane, I'm moving in 3D. It's the integral of this form, and that comes directly from this. Now, there's a common mistake is people want to integrate f dot r. No. You would only do f dot r if f and r were both constant. Because otherwise you'd get variable things that aren't really useful. Otherwise you have to integrate because, again, as I'm moving, I have to have small incremental changes. So this is work, and that's what a work integral actually looks like. So that's kind of nice. Now that's not the only form, but that's the form that we use the most often. There is another form that we sometimes will see, and this is something we're going to use later, all right? If you remember, let me erase this over here. The way we derived curvature, do you remember curvature? We said curvature was the rate of change of the direction of the unit tangent as I was moving along an arc. So remember, the definition of curvature had to do with dt ds. And then we used chain rule to go, oh, dt, ds, dt. We were able to figure it out. But this meant the rate of change of the direction of the unit tangent with respect to every incremental change in the arc length. So if I move one unit along the arc, if I did a huge change, we'd say there's a lot of curvature. As I move one unit along the arc, if I barely moved at all, right, in terms of my direction, we'd say there's little curvature. In fact, if I'm on a line, we'd have zero curvature, okay, because it's not changing direction at all. But we parameterized this with respect to the arc length parameter for the purpose of creating that. Did we ever actually do calculations with this? No, but that was part of it. So it's the same sort of thing here. If I want to do, let's see, we defined, therefore, the unit tangent was, let me back up here. Sorry, the unit tangent as a function of this, we did this at the beginning of the semester, right? So there was a dr dt and a ds dt, and oh yeah, okay, there was all that stuff at the beginning. But this would therefore be dx ds, dy ds, dz ds, okay? So if I did this, f dotted with t, which is the same as f dotted with dr ds. Now, dr ds is not the same as dr dt. dr dt, okay, dr dt is length per time, so that would be velocity. What's dr ds's units? Length per length. Yeah, the rate of change of my position with respect to unit. Ooh, so that's not going to, ooh, boy, how do I get force from here? Easy, or excuse me, work from here, easy. I integrate this with respect to s. Does everybody see that? Oh, okay, now I'm back to, except we're going to write it this way. We're going to write this as f dot t ds, which is a really odd way of looking at it, but that's exactly what it is. When I go into three-dimensional, certain types of motion in 3 dimensions, we're going to find it's actually easier to do that last integral. Okay? Again, it's a context thing. This is the thing you're going to do most often. But that is an alternate way. This is also work. I just showed you the development. So there's another way of doing that. And the cool thing is, if I use the same notation that I just did here, okay, now look at this for a moment. If I take my m dx ds plus n dy ds plus p dz ds, and then I integrate with respect to s, what am I going to get? That. I'm going to get it back again. Okay, so I'm always going to come back to this. That's kind of a good thing. So let's do an example of how we would use all of this. So let me, example written down here. Let's do a 2-dimensional one, then we'll do a 3-dimensional one. All right? Weird one, but it's a very short interval of time here. All right, what I want to do, I want to calculate the work. Okay, this is a strange path. Can anybody tell me what this path is? It's not a circle. How do you know it's not a circle?
Not equal coefficients.
Yeah, so what is it instead? Yeah, how about if I wrote it this way? X over 3 equals cosine of 2t, y over 2 equals the sine of 2t, so that squared plus that squared equals 1, this squared plus this squared equals 1. Oh, it's an ellipse and they have different denominators, that's why, okay, it's a little bit more long. It's an ellipse. So the parameterization for an ellipse and a circle are very, very similar. And it's just a short, tiny piece of this ellipse. I'm moving along an ellipse. In fact, what does the ellipse look like? Something like this, right? I do circles better. And I said from pi over 4, excuse me, from pi over 12 to pi over 4, so we're somewhere in here, right? Just a short chunk of this thing here. And I'm applying this force at every point. We need a few things. I want to do this problem. Well, we lack a few things. Tell me one thing we don't have yet. We don't have an R of t yet. Can we make one really easily now? Yeah, I told you what x of t and y of t are. So let's define our R of t. So R of t is what? It's 3 cosine of 2t, comma 2 sine of 2t. Why do I need an r of t? Because I need to take its derivative. Ooh. Okay, so I need a dr dt. And what will that be? Talk me through this. Anyone?
Negative 6 sine.
Negative 6 sine of 2t,
4 cosine.
4 cosine of 2t. Beautiful. All right. So now I'm going to do the dot product of this guy, and then I'm going to integrate, right? Right? I'm thinking with my left eye, so you know something's up. Why won't that work?
Have the same variable?
Yeah. Or just simply too many variables. How many do I need? Just one. Oh, okay. So who wins, X, Y, or T?
T.
Probably T. So what do I do? These X's and Y's are going to get replaced by these guys. Okay, so the force is the force, okay? I'm giving you a force vector. Aren't there an infinite number of paths I could travel on? But I'm giving you the force vector. There's an infinite number of paths. The paths will determine what I'm going to replace X and Y with. So if I've given you a different path, maybe I'm moving along a parabola, I don't know, I'm giving you a different path, then that's what I would substitute in here. So I'm going to substitute these X's and Y's into here, so my F will now be a function of T, then I can do the dot product, then I can do all the calculations. That's not complicated, but it's something you haven't done yet, so we got to kind of figure it out as we go here. So let's define now F of T, because technically that's F of X of T comma Y of T. That's really how we're viewing it in the first place. So what's this going to be? So what have I got? I got 2 times X times Y, which would be
12 cosine 2t sine 2t.
so 12 cos 2t sine 2t. Oops. No comma there. And then 4y cubed. What will that be?
32 sine cubed of
32 sine cubed of 2t. Beautiful. I'm not taking the derivative of f. No, I'm going to do the dot product with f and dr dt. The only mistake that tends to be common here is people forget to find dr dt. They use the r instead of the derivative. So I need the derivative. All right, so let's do it. What is my f dotted with my dr dt? This is going to become the integrand when I am finally able to find the work. So when I do this, what am I going to get? So what's this? Negative 72 cos 2t sine squared 2t. And then what? Plus 128 cos 2t sine cubed 2t. Does that look right? Hopefully. Hopefully don't have any boo-boos. I think that's right. Yeah, it looks reasonable. I'm now going to integrate this. Is this going to be an easy or a hard, or do I have to do some weird substitutions? What do you think? How about if I do this? Work equals the integral from what to what? So those bounds are still important. Of this, you know, what if I factored out the cosine term? What if I wrote it like this, just for the heck of it? Negative 72 sine squared 2t plus 128 sine cubed 2t all times the cosine of 2t. Why would I do that? Tell me why I would want to do such a crazy thing. Sine cubed and sine squared. Is this a simple u substitution? Yeah, what's your u though? probably let u be sine of 2t. Oh, then what's your du?
Cosine
Cosine
2t.
of 2t, oops, cosine of 2t, I'm leaving a little space there,
2.
times 2. Oh, so I need a 2 there. Negative 72u squared plus 128u cubed du. We can change the variable at this point. Can we just integrate that though? Is this one of those that is just sitting right there in front of you kind of thing like we talked about yesterday? Yeah, I think anything you do that is valid, you know, if I do a correct substitution, change the variable, change the limit, that's all okay, but it's kind of long. I see negative 72u squared plus 128u cubed. What's the antiderivative of negative 72u squared? That'd be negative 24u cubed, right? What's the antiderivative of 128u cubed? It'd be 128 over 4, or 32u to the 4th. I still have a 1/2, and it's still pi over 12 to pi over 4. Oh, okay. I can change the variable and do all that stuff. That's always correct. But this one, because the chain rule factor, this is right there. I don't have to do anything clever. Pi over 12, that's not a common angle. How are we going to deal with that? Well, it's 2 times pi over 12. Ah, that does produce a common angle. What is the sine of pi over 6, anyone?
1/2.
That's only a half. Yeah, that's a happy one. And 2 times pi over 4, what's the sine of pi over 2? 1. So I have really nice numbers here, don't I? I have really nice numbers. So I'm going to get negative 12 times, I'm going to write it this way, times the sine of pi quantity cubed, just so I don't mess up my interpretation, plus 16, I'm distributing at 1/2, times the sine of pi quantity to the 4th power, minus negative 12 sine of, what did we say, pi over 6 quantity cubed, plus 16 times the sine of pi over 6, oops, quantity to the 4th power. I'm writing it like that to remind, did I lose something?
Pi over 2. For the first 2.
Oh, thank you, pi over 2, sorry, pi over 2. And does this look right?
Yep.
Now, I'm writing it in this form to remind us that I calculate the sign, then I raise it to the power. Sometimes people do weird things like they raise the argument to a power and then take the sign of it, or something wacky like that. Remember, the sine cubed means it's the cube of the sine function, not the cube of the argument. Now, the first case is easy because these are all 1s. But the second case, these are halves. Oh, so that exponent really does matter, doesn't it? So what do I have here? Well, that's 1 to the 3rd power. That's 1 to the 4th power. So all of this is simply 4. Nice. What's this though? That's 1/2 to the 3rd power. That's 1/2 to the 4th power. Ah, that's different. So 1/2 to the 3rd is 1/8. Negative 12/8 is negative 3/2. 1/2 to the 4th is 1/16 times 16. So what do I have on the right here? I have a negative 1/2, and I'm subtracting it. So what is my final answer? It's going to be 4 plus 1/2. Yes? So my answer will then be 9/2, which is kind of strange. You wouldn't have figured that you were going to get a nice, happy, rational number with limits like that and functions like that. This one came out pretty nice. Okay, a lot of algebra, but nothing was terribly hard. So the idea is, you're given a force. You can't do anything with the force. It's just, here's my force. Here's how much force I'm applying. So Dean in here says, okay, here's how much force I can give you, Mr. Brown. In every direction, I'll give you this force. And now what I'm going to do is give you a map of what I want you to do. Okay? But if I give you a different map, will it be a different answer? Yes, but it's still applying the same force. That's the thing that's confusing at first. The force doesn't change, the map changes. That's your R of T. That's where I want you to go once you apply this force, okay? And that, could I do this problem and get a negative number? Could I do this problem and get a 0? Sure, it depends on everything. A lot of it depends on the path and things like that. So let's do one in 3D now, because that's the most common problem. The 2D is nice because I can draw a picture. But conceptually, it's not hard to do this in 3D once you understand what it is you're finding. All right, so give you one that's a little bit busier. The last statement is kind of an odd statement. I said you're starting at this point, you're finishing at that point. That can't be random. There must be a value of t that produced each of these points. Everybody follow me on that? If I just randomly made up an ordered triple, it wouldn't match this. So when I'm looking at this going, okay, let's see. Right now, 1, 2, 4, I'm pretty sure this means that t equals 1. Because if t equals 1, I have 1, I have a 2, I have a 4. How about the next one? If t is 2, then that's 4, 4, 2. Okay, that's t equals 2. Wouldn't it have been just easier for me to say t is going from 1 to 2? Yeah. But I'm showing you, I could have also told you your beginning and your ending point. If I gave you an ordered triple that there's no value of t that would have produced it, then walk away from the problem. It's now impossible. It's not possible to come up with this situation. So if I said t is going to range from 1 to 2, or t is going to start here and end here, it's the same thing. Okay? I just have to be able to interpret it that way. Anybody follow that? That's really huge. So now I need to define an R of t. Then we're going to change f to f of t, just like we did in the previous problem. Then we're going to do all of our stuff. So what is my R of t? You just take this. There's no interpretation necessary. I take my given. So dr dt, okay, what's dr dt? Not 4.
Negative 4 over t squared.
Yeah, t squared. Ooh. Think of it as 4t to the negative first. Oh, exponent, okay. Otherwise, I might make a boo. All right, lastly, what is f of t? I mean, the only calculus I've done so far is I took a derivative of r of t. That's just not, that should never be challenging. Now be very careful. If I don't do this perfectly, I'm doing now a very, very different problem with a very different result. So x is t squared, y is 2t, so this is the square of t squared times 2t. Okay, let me write down. The square of t squared times 2t is what?
2t to the 5th.
That's 2t to the 5th. That's my first component, okay? I'm not above writing it down. Most of you won't do it. You'll do it in your head, won't you? I always love it. And you're going to be right 99% of the time, which means you're going to be wrong 100% of the time. You can't have 1% error because it means you're doing a different problem. So, next one. 2yz. So I have 2yz. What's that?
16.
Oh, that's just 16. I like that. Okay, that was easy. And then the third one, I have 3z. Oh, geez, that's easy. What's 3z? 12 over t. Great. We are ready to rock and roll. Give that color a break. So, f dotted with dr dt. This is all my scratch work. I would hesitate to say I have the integral of the dot product, then do the dot product, then simplify it all while you're still in the integral. No, do all of this first and then write your integral. Otherwise, it's kind of hard to follow. So that's the given. I created that. I took the derivative. I rewrote this. Now I'm doing this. There's no integration yet. We'll finish this part completely. So I made it really easy on myself here. So what do we got here?
4t to the 6th.
4t to the 6th
32.
plus 32
Yeah.
minus
48 over t.
48 over
T factor.
t cubed. Oh, careful on that one. 48 over t cubed. Would it be okay, just because I'm going to have to integrate later, would it be okay if I wrote it like this? Would there be anything wrong with that? For the purposes of integration, might that be a good idea? The problem with having something in the denominator and you're trying to integrate it, you see a positive 3 as an exponent, don't you? And therefore you may integrate it as a positive 3 when it's actually a negative 3, and that changes things. And so a lot of times we're too good, we're too fast, and we're looking at the quotient not realizing that it's a negative exponent. So it might be safer to do that. As long as you get the right answer, I don't care. But if you get the wrong answer because you forgot that, no good. All right, so the work is the integral from what to what?
1 to 2.
1 to 2. Of all of this. Wow, that's just not complicated. That's a pretty happy problem at this point. So what do we get? 4/7 t to the 7th plus 32t.
Isn't it?
Oh, I think
Negative
so.
3?
Negative-
Oh, did I mess up?
Yeah. The
Yeah, negative 3
negative
to the
three.
negative 3.
48t to the negative 2 right there.
Oh, thank you. That's okay, right? I didn't write that down correctly. did I?
Everything's good.
Okay, all right, and then the last one, plus,
12 t to the minus 24.
careful, you gotta add 1 to the exponent. So 24 t to the negative 2, or 24 over t squared. Now I'll write it that way. And I'm going from 1 to 2, okay? So, get out your calculators. My answer is a rational number, but it probably has a denominator, of 7, doesn't it? Because everything else is going to come out really nice. Now, you want to be really lazy? Do you have to use your fraction key? No, just calculate the whole thing as a decimal and then do what? Multiply your answer by 7. Because you already know 7 is the denominator. Again, remember I showed you guys that before. Equidecimal on top, equidecimal, sorry, let me rewrite that. This equals equidecimal, which is something over 7. You just multiply equidecimal by 7 and then you get your numerator. Does that always work? To a point. If your numerator or denominator is too large, most fractions or most calculators won't store past a certain number of digits. If I have a 5-digit numerator and a 5-digit denominator, unless you have a TI-89 titanium like me, yeah, I got one of those. It probably isn't going to save. It's probably going to convert to a decimal.
Sorry, why did you divide 48 by 2 and not by 4?
Because the antiderivative is t to the negative.
4.
Add 1 to the
Oh,
exponent.
okay, never mind, sorry.
But that's the whole reason, Nina, we wrote it in this form, so we'd go in the right. It's funny, we wrote it this form so we would go in the right direction, and half of us still went the other way anyway. Where you add 1 to the exponent. So what do you got?
410 over 7.
Sorry, I couldn't read.
410 over 7.
Does it make it a
I
difference?
got 606.
I also got
I got
606.
6.
Okay, apparently they don't like your answer. I like your answer. I think it was a great answer. I think that one's probably a better answer though. Is this problem hard in general? as a general thing. Not really. What would make it hard? Well, you get to this point and you have something that you're not sure if you can integrate or not. Is that possible? Yeah, but you'd have to have something kind of nasty here. So for example, what if this here was nice and happy, but these guys here were trigs and e's and all sorts of O's. Then when I go to substitute, I might have some really terrible functions, right? Lots of compositions of functions. That's possible. I don't think you're going to see any of those in a calculus textbook, though. Because again, the idea here is to navigate through the problem. If you have things that you can't integrate, then you reach dead ends, right? There's nothing you can do, okay? So the concept of calculating the work, and all of these are work-related, is simply I'm going to do an integration in the end of a dot product.
Is there any way to, like, you get your answer and, like, gauge whether or not you think that it is a good, or like
Oh, that is the million-dollar question. It kind of, let's take a step backwards. Let's think Calc 1 for a moment. You're doing your problems, you're integrating, you're getting answers. And there's no application, you're just integrating, you're getting answers. You can use technology to check your answers sometimes. You go, okay, I did my integration correctly. Now you get to the application problem. So now there's certain things you know. I'm calculating the volume. On the quizzes, I'm cracking up on quiz 19. About a fourth of all the volume answers were negative. Come on. You got to know when you're turning in a negative volume that there's an error somewhere. You go, it can't be negative. So what did some people do? The answer is negative 300 equals positive 300. There, that's how I'll fix it. Well, it was the wrong number to begin with, but yeah, you can't do that. I know some kind of answers have to be positive, for example. I'm finding an area, an arc length, a surface area, work, anything. Now, we know that certain things could be zero, or things could even be negative, and there's the rub. So now, let's fast forward to Calc 3. We did a motion problem. Okay, what is the impact speed? It can't be slower than the initial speed, can it? So if I made a mistake, and by the way, it's not that unusual if somebody makes a mistake and they have one that's slower, but that's the one that sets off the red lights. Problem is, if you have an incorrect answer that's still logical, that's the one that you can't find. So I always say, does your answer make sense? Would it work? And you say yes, then you have to go with it. Because there's no absolute check. And because we don't have units of the situation, we don't know what we're supposed to get. Could we get a negative answer here? Is that possible? Could we get zero? Yeah, we could get zero. Okay, that has nothing to do with being conservative, by the way. We could get zero. All things are likely. So unfortunately, I can't look at that number and say, oh, that's a great answer or that's a bad answer, because I don't have any context to put it in. And I know that's not the answer you wanted to hear. But in this case, we don't have a situation. There's no application. So there's no units that I can apply. But if it's a situation like a surface area problem or a volume, now you have certain constraints. You can't get a zero. You can't get a negative answer because you have a physical shape. That's about the only one. Now the problem is, what if your answer is astronomically large or infinitesimally small, and you're going, oh, I don't know if it's supposed to be. Can't tell you how many times in a calculus class someone will dismiss an answer. They go, oh, that just seems way too big. I went, really? What's too big? You were doing an integration of a polynomial of a high degree, a definite integral. You're probably going to get a really large number because you're raising things to large powers. And a lot of folks will say, well, I got a ridiculously large number. It can't be right. Why can't it be right? But you're saying, wait a minute, I'm finding an area that's completely in the first quadrant or something like that, and I'm getting a negative answer in the end. I know I've made a mistake. There's some things that do stand out. Okay, now, what if, give you an example yesterday, I got to push my wheelbarrow, I have the minefield laid with barbed wire, or I have the gumdrops and butterfly path. And what if it didn't matter? What's the only time it won't matter? Talked about this yesterday. If I have a conservative force, it won't matter. It only matters about the displacement, where I begin and where I end. What if you have a conservative force? Then is all of this necessary? This isn't a conservative force. But if this were a conservative force, what's the only thing that really mattered? Where I began and where I ended. The path itself is not all that important. That's an interesting concept, isn't it? that the path wouldn't be all that important. So let's do an example of something. Okay, I want to show you this, because this is leading into the next big thing, okay? Do something relatively simple. Okay, I'm gonna do a two-dimensional problem. Okay, that's what I want. Now, I'm going to keep it simple. Okay. I'm giving you a force, and I'm asking you to calculate the work done along each of these paths. And you have nothing else to go by except, okay, I'm gonna do kind of the same problem 3 times. Not exactly. That's kind of what's going on, okay? That would be C1, C2, C3. Okay, are we all together on this one? So, let's do C1 first of all. So on C1, what parameterization, and by the way, in all 3 cases, because I wrote y as a function of x, in all 3 cases, the only thing logical is to say let x be t. You don't have to. But there's more algebra involved if I choose y equal t, okay? You know, square roots, and yeah, I don't want to do that. So x equals t, y equals 4t, and t will range from what to what?
0 to 2?
0 to 2. I think that's going to be the case in each one of these, isn't it? All right, so my r of t is, where is it? My r of t is t 4t. So my dr dt is 1, 4. F of t, all right, so let's go over here. Don't be in a hurry, because we want to get this right. So x is t, y is 4t. So x is t, y is 4t. So this would be 3t squared times 4t plus the square of 4t. What would that be? 12t cubed plus 16t squared. Does that look right? We good with that? Okay. And then over here, I have t cubed plus 4 times t times 4t. That would be t cubed plus 4t squared. Okay? So now what is f dotted?
Yeah.
Oh, did I drop them?
2 should be 32 t squared.
Oh, hold on, which one?
The
X,
x.
it's 2y squared, not just y squared.
Oh, here.
Yeah,
Ah, thank you.
and then after that, 32.
So, is the other one okay? Did I mess them both up? Let's do that. So what is that? That's 12t cubed plus 32, help me out here,
T squared.
t squared And then what's the next one? T cubed plus 4 times t times 4, 16t squared. I don't think I got either one of those right, did I? Okay. Does that look right? I'm relying on you guys as my proofreaders here. I think that's probably okay. All right. So let's do f dotted with drdt. Well, that makes it easy. Times 1. So that's 12t cubed plus 32t squared plus 4t cubed plus 64t squared. So that's 16t cubed plus 96t squared. Does that look right? We good? Okay. So the work done is the integral from 0 to 2 of this. So that's going to be 4t to the 4th plus 32t cubed from 0 to 2, which would be 64 plus 256 or 320. Okay, great. Boy, it came out really nice. Got lucky. Okay? Now, let's do the second one. Okay, what parameterization do I want to use on C2? X equals t, y equals
T squared.
2t squared. And t is going from 0 to 2. Okay? So r of t is going to be t 2t squared. dr dt is going to be 1 4t. Okay? Go slow because, well, even slowly we can make mistakes. So, x is t, y is 2t squared. So this is 3t squared times 2t squared. Plus 2 times the square of 2t squared. Is that right? That look correct to you? Okay, so what do we got? We have 6t to the 4th plus 8t to the 4th. Yes? So 14t to the 4th? And how about here? I've got t cubed plus 4t times 2t squared. T cubed plus 8t cubed, so I got 9t cubed, I believe. This one turned out to be a little simpler than the other one. Does that look right? Again, if I have an error, I need you guys to catch it. We don't have errors on purpose, we just have errors. Okay, I think this is good. Let's see. Okay, so what is f dotted with drdt? That's going to be 14t to the 4th plus 36t to the 4th, which is 50t to the 4th. Very nice. Okay, so far so good? So my work is going to be the integral from 0 to 2 of 50 t to the 4th dt. Wow, that is a friendly integration. All right, so what do we get here? So this is going to give us, what, 10t to the 5th from 0 to 2, so 10 times 32, or 320. Huh, who knew? Okay, let's do the third one. That shouldn't be too difficult. So I've got x is t, y is this time t cubed, and t, of course, is going from 0 to 2. My r of t is t comma t cubed. So my dr dt is 1 comma 3t squared. Okay? Now we need our f of t. All right. Need more erasers. All righty, so t and t cubed. So we are 3t squared times t cubed plus 2 times the square of t cubed. Over here we have t cubed plus 4t times t cubed. I believe that looks, is that correct? Everybody? That look good? So 3t to the 5th plus 2t to the 6th let's see, plus, actually you guys need to tell me, it's too far away. What's here? 2t to the 6th, okay, and then the next one is?
T cubed plus 4t to the 4th.
All right, you all agree with that?
Yeah.
And no boo-boos. Boo-boos are unacceptable. Okay. So f dotted with dr dt, this one's a little more complicated. I'm going to get 3t to the 5th plus 2t to the 6th plus 3t to the 5th plus 12t to the 6th. So that ends up being 6t to the 5th plus 14t to the 6th. Wonderful. So now my work is the integral from 0 to 2 of 6t to the 5th plus 14t to the 6th. That would be t to the 6th plus 2t to the 7th from 0 to 2. And that'd be 64 plus 256, and that's, so work is always 320 no matter what the question is? Is that how this works? How could this be that we took 3 different paths and got the same answer?
Work is force over displacement, not force over distance.
Force is conservative.
Maybe that's the reason. If, generally speaking, if I change the path, I'm going to change the answer, generally. But I just did 3 paths, kind of lucked out that all the integrations were simple. They weren't hideous fractions. So how could I have known, because this isn't a vector in R3. Remember, in R3, you just have to do the curl. This isn't a vector in R3. This is a vector in R2. So I'm going to show you something. So do we all agree that 320 is kind of a magic number for this problem? Okay, let's bury that part. I'm going to show you something, okay? I'm going to start with a potential function f of xy. It could be anything on planet Earth. Then my f, which is the gradient of f, that's my m, that's my n. Agreed? That's the way we usually write it. Tell me. What's the partial of m with respect to y? Wouldn't that be f xy? Yes? No? Maybe? What's the partial of n with respect to x? So it'd be the same thing, wouldn't it? It's an absolute black and white statement. If you start with the potential function and you find its gradient, that is a conservative vector. That's the definition of a conservative vector, that it came from the potential function. Except you don't have access to the potential function. You're just starting with a vector. How the heck are you supposed to know then if it's conservative or not? If, then. If this partial equals this partial, it is conservative. Period. If they're not equal, it's not conservative. So now let's go back to here. Here's my m, here's my n. What is, and you can write it this way if you want, what's partial of m with respect to y? It would be 3x squared plus 4y. All right. What's the partial of n with respect to x?
3x squared plus 4y.
Oh my gosh. This was conservative, wasn't it? But that's how we show it's conservative. We don't show it's conservative by doing all of this work. So then that begs the question. Okay, I think Zachary said something about displacement is the only thing that really mattered, but only because it's conservative. We couldn't have started by assuming that, because that isn't, if it's not conservative, then there's more than just the displacement. So that means if I had known what my potential function was, then all I would have had to do is evaluate my potential function at the starting and at the ending. That's literally all you would have had to do. Well, I wonder how would I find my potential function? Well, remember, now we know there is this. Agreed? We know there is this. So what is this? This is fx. What is this? This is fy. All I have to do is integrate. I only have to integrate. And I'm going to show you. This is a process. It's not a complicated process, but it's a different process. Now, which one do I integrate? Doesn't matter. See, if I integrate this one with respect to x, I'll get back to here. If I integrate this one with respect to y, I'll get back to here. You never do both. Ever. Because you can't take two different answers and compare them. It won't work ever. And I have, having said this, and going through this a million times, I will still have people go, no, I saw this, literally, they'll say, I saw this YouTube video and they did it this way. And then they get the wrong answer on every problem. They can't figure out why. No. You integrate one of them. That's it. Question.
So you only integrate it if it's conservative?
Yes, because let's go backwards a step. We just determined that this is conservative. What does that mean? That means there exists this guy. He exists. We just don't know where it is, what it is. But we all agree now that it exists. Why? Because that makes this the gradient of this. We know that. Why? Because the cross partials were equal. If these weren't equal, it's not conservative, there is no f of xy. So there's nothing to do at that point. And that's, by the way, the vast majority of all things are that way. Okay? Second.
Check our work, if we integrate one, can we then take the derivative of that?
Well, hold it. You're kind of giving me a blueprint of actually how to do the problem. So I'll show you. Checks are built in. Checks are easy. Because when you integrate something, how do you always check it? You differentiate. The most common errors you're going to make are more likely plus or minus sign. You have a sign X, a sign Y. Yeah. The most common errors are really silly errors like that. They're not really big whoppers. So, f of xy equals the integral of 3x squared y plus 2y squared dx, or x cubed plus 4xy dy. You do one or the other, you do not do both. You do one or the other, you do not do both. Not even as a check. You'll end up doing so much extra work that's unnecessary. I am a creature of habit. And what I mean by that is, if I have a bunch of similar problems, I will attack all of them the exact same way every single time, because then you become more efficient. You will find that there is no advantage gained by doing one versus the other. You say, well, what if one has a really nasty function, the other one doesn't? You're going to end up integrating everything at some point anyway. You can't avoid nastiness by choosing one versus the other. Does that make sense? It's still all going to be there. So I tend to just take whatever one was first, every single time. And it will not change the number of steps the problem has. But if I do it the same way every time, then it starts becoming automatic. I can navigate through the problems pretty seamlessly. So I'm going to integrate this thing with respect to x. And when I do that, what am I going to get? With respect to x.
X cubed y plus 2xy squared.
2xy squared. But this is an indefinite integral, isn't it? So is there a plus something?
Plus C.
Plus C.
Are you sure?
No.
This, whatever this is the partial with respect to x. So if this had any constant terms, they'd go away. That's why we put the plus c. But what if this had pure y terms? They would also go away. So we don't put plus c, we put plus g of whatever the other variable is, because there might be a pure function of y there. Ah, that's what we do. Now, I don't know what the plus is. Well, how am I supposed to find it? Because the partial of this with respect to y absolutely gives me this. This is the algorithm. This is how you do all problems. You do them all the exact same way. You don't know what lives here. Heck, could this be 0? Yeah. But what it can't be is anything with an x in it, because you already integrated with respect to x. You've got everything x-ish that exists. Okay? So, now I'm going to do the following. So follow me here. Partial with respect to y of that is x cubed plus 4xy plus, how about g prime of y? I can say prime because g is a function of y only. It's not a partial derivative. Now, what must this be equal to? This must equal n. Exactly. It absolutely must equal n. So I will set them equal. If I have made an error, then I will have an impossible statement here, mathematically. And every now and then, you're going to make a mistake and go, oh, that's not going to work. Let me go back and fix my error. Now, what do you notice? G prime of y is 0. Great. So therefore, g of y is, no, the antiderivative of 0 is not 0. Only the derivative of 0 is 0. Antiderivative of 0 is
What?
constant.
Does that have anything to do with the C1, C2, C3 starting points in 0, 0?
No. No, I did that just to make the problem easier. The question was, is anything we have over here, does that have anything to do with this? This does not actually come into play yet. What if I said start at 2, 8, and then end? Now, the reason I went 0, 0 to 2, 8 is because those are the only ordered pairs that all three of these intersect at. That's why it was also easier for me to do this in my head if I started at 0, 0. Okay. I'm not that clever. I said, let's start at 2, 8, and then let's end somewhere else. That would have been a lot more math. Do you understand? You're like, oh yeah, that would have been really complicated. So, this is great. Therefore, I can say my f of xy, my general antiderivative. Great. Now, why is this important? In count 1, when you integrated, you evaluated your antiderivative at the endpoints, didn't you? At the limits of integration. But why, and some people forget this part, why in count 1 do we just pretend that c isn't there? No, we don't pretend c is there. In fact, you should have been told this verbatim because there's only 2 times in your math lives the following will ever happen. The second time, it'll happen in differential equations. When I find a general antiderivative, I have to have the plus c because every constant would be a valid answer. That's really important. When you do a definite integral, every value of c gives you the same definite integral. Why? Because you have stuff plus c minus stuff plus c. So no matter what value you chose for c, what always happens? It will cancel. And since every value of c in a definite integral gives you the same answer, doesn't matter what value you use, they'll always get the same answer because your c's will cancel. In a definite integral, you don't ignore the c's. That is incorrect. That's bad mathematics. You get to choose the value of c. There's a very, very important problem in differential equations that is really similar, where you get to choose the value of c because all values of c produce the same final answer. Therefore, when you get to choose the value of c, what value will you always choose? You will choose c to be 0. You do not ignore the c, drop the c, pretend it's not there. No, you're actually choosing c to be 0 because all choices give the same final answer in a definite integral. In an indefinite integral, you don't get to choose c. Well, how do I find c in an indefinite integral? You have to have an initial condition. Remember that? Oh, and now I can find the specific value of C. But if you don't have an initial condition, you just leave it as a plus C. So we will, when we do our integration, we just did our integration, excuse me, when we do our evaluation, we will choose C to be 0. Because it's not going to change the final answer. So you're going to like this. Okay? Where did this problem start? Started at 0, 0. Where does the problem end? 2, 8. So the work is going to be x cubed y plus 2xy squared evaluated from 0, 0 to 2, 8. You notice I did it as ordered pairs because that's my starting and ending, not a value, a place. Well, I'll do this one. Okay, I got this one. You guys got this one? All right, you guys do this one. Evaluate this at 2, 8. What do you get?
3.
No way. Yeah. You like that? Why did I get the same answer no matter what I did? Because we said the force was conservative, therefore the integral is independent of path or path independent. That's the same thing. It's the same. Some people say path independent, some say independent of path. You know, it's kind of like the whole rotary boat thing, you know, which side they're on. I never actually had to do the work. All I had to do was find the potential function and evaluate it, which usually is going to be easier. Usually. Okay? You with me on that? Now, when can I do this? Only if the force is conservative. If the force were not conservative, then everything we did, this is what we do in every problem. This is always the path. But if you have a conservative force, you can just do it by an integration. Now, this process here might not be difficult. This was not difficult on any of my 3 paths. This was because I used fairly friendly numbers. And most of the time, that's probably not going to be that difficult. But the fact that I could get it in an alternate way that did not involve any dot products or any, you know, I didn't do derivatives. I didn't do all that stuff to get here. It's crazy. It's cool, isn't it? So if the there's some language that people always get confused on. If the force is conservative, the integral is path independent. The force isn't path independent, it's a force. It's just a force. But the force can be conservative. Okay, so when I said I want you to move that wheelbarrow from point A to point B, if you have a conservative force, then all that matters is where's point A and where's point B. The path you took to get there is irrelevant because all paths would produce the same final answer. And that's kind of cool because sometimes the paths can be kind of complicated. Okay? None of these were, but we could have made this complicated. Well, what do you mean? What if I made these complicated through some exponentials and inverse trigs and stuff, but still had me starting here and ending here? Those integrations would have been gnarly. And I still would have got 320 as an answer. Okay? So, let's try another one. So I'm going to change the way the question is asked slightly. Okay, give me just a second. I don't want this to be real complicated. Keep this relatively simple. All right, I'm giving you a force vector. I'm not giving you a path right now. That's going to come later. What I'd like to know is this vector conservative? If it is, let's find the potential function. Then any question I ask you regarding this, okay? So that's kind of the example I did earlier with Nina. I said, you have your force vector. That's unchanging. I'm now going to give you a map and say, go from point A to point B. But if your force is conservative, then the route you take is irrelevant. Everybody understands that. The route doesn't matter. But what if your force is not conservative? No, then the route you take is everything. Okay? Because every route would produce a different answer. That's why it's so necessary for us to determine conservative, and if it is, to then find that potential function. Yeah, Katrina?
In the real world, what does a conservative force look like? Like, how could it not matter what path you take?
Well, again, the idea of conservation of energy, that kind of thing. A conservative force, in this sense here, says it only matters the displacement. Okay, that's what we just showed in the previous example. That's why we only cared where we began and where we ended. Do you want to try it?
Yeah, it's like if you have a roller coaster and you have the same starting height and ending height, it doesn't matter what you do in the middle. At the end, your speed is going to be the same as long as you make it to the end, because the only force acting on it is gravity. So when you're going upwards, you're gaining gravitational potential energy, and when you're going downwards, you're turning that energy into speed. So at the end, all that energy is conserved, so the speed at the end will be the same, no matter path. So conservative just means like, when you're going upwards, you're gaining gravitational potential energy, so that total energy of the system is still the same. Because whatever you lose in speed energy and kinetic energy from going upwards, you gain in potential energy. And then when you're going downwards, you're losing potential, but gaining it into speed. So at the end, you're gonna have the same total energy as the start.
I like that. This isn't a physics class, so sometimes it's harder because we're not doing a boatload of physics applications. We're doing all of the math required to do the physics later. How many here have not yet taken 195? I know I asked you that. So in other words, some of this stuff might be a little bit over your head because you're going, well, I haven't done any of this yet. But for those who've taken 195, this stuff becomes kind of second nature, doesn't it? You go, okay, that's why. It kind of helps you explain some of the things. Unfortunately, Calc 3 explains the things in physics, not Calc 2, really. Yeah.
Wouldn't it be the same as saying there's no friction, like no drag force, no like external forces, it's just this thing going through space and nothing is opposing it. It just
That's
makes
a
no
good way to think, like in a vacuum.
Yes.
Okay, you could think of it that way. Maybe in a vacuum, that works fine. We don't live in a vacuum, but so the idea is, I'm not trying to give this a picture or a physical meaning, like I actually have an object that I'm measuring the force. I'm just saying, here's a force vector, and then we're doing this very abstractly. But those of you in physics, you're going to do this. You guys remember the pulleys? Oh, don't you hate the pulleys? And they're all in different directions and different angles. But the idea being, with the drag, if I can reduce or eliminate essentially the drag, then things work really nicely. But when I have to calculate all those other things in, it's a little nastier. I would like to, basically, my end result here is, at some point, I'm going to give you a beginning and an ending and potentially a path, and say how much work is going to get done, okay? Are you going to have to do it the long way, or can you do it by integrating this? Well, integrating this is meaningless to find it, in other words, to find the F if it's not conservative. So my first goal is always to check for conservative. So how do I do that? You take the curl vector, okay? Turns out the test in 2D was real easy, wasn't it? Was my equal to nx. That's all I needed to do. But the curl vector has 3 components, so I actually need to do the curl. So, all right, so. All right, so the partial with respect to y is what? What's the partial with respect to y?
-8z.
Negative 8z. Minus, and what's the partial with respect to z? What's the partial with respect to z? Negative 8z. Oh, okay. Partial with respect to z minus the partial with respect to x. Oh, there's nothing there. Okay, a little good. The partial with respect to x, oops, minus the partial with respect to y. What do we got, folks? We got the 0 vector. Crowd goes wild, right? Confetti everywhere, dancing in the streets. I got the 0 vector. What does that mean? that means f is conservative. So your conclusion right here is f is conservative. To try to find a potential function before you've determined it's conservative is a waste of time because the potential function might not exist. And boy, you're going to be beating your head against the wall trying to find this thing that actually can't be found. Sometimes we skip this step. This is a critical step. It's not a hard step. What if 2 of the 3 were 0? What if 1 of the 3 was 0? It's the 0 vector or it's not the 0 vector. It's the 0 vector, so that means there is a potential function. There is a function up there that we can't see where whatever that function is, this is its partial with respect to x, this is its partial with respect to y, this is the partial with respect to z. So I now need to work backwards through integration to figure out what that potential function is. This is not a difficult process, but it will involve 3 integrations. Okay, I'm going to have to integrate with respect to x, y, and z. So the easiest way, like I said before, is I just start on the left and work my way. Okay, I'm going to get the same answer regardless, but I always like to do it the same way just so I can keep up, not get lost in the process. So f of x, y, z equals the integral of 2xy dx. Because this is the partial of f with respect to x. That's why I can only go backwards by integration. And so what does this give me? X squared y, great. So that's my f. But I'm looking at that. If I start with x squared y and I take a bunch of partials, I don't think I'm going to get that. Do you? No, I don't think so. Because there's still more stuff. Oh, plus. What variables can still show up? Y and z, can't they? Okay, so if I had something, let's say I have a pure y term, I have a pure z term, or I have a combination y-z term. Wouldn't that derivative have been 0 with respect to x? So I never would have seen it. So what we do here is we say plus g of y comma z. Not plus c. It is most definitely not a constant. I don't know. I'm not a rocket scientist. I play one on TV, but if that was a plus c, I don't think we'd get any of those other terms like a sine. They got to come from somewhere. Okay, so now the next thing is, what is the partial of f with respect to y? I move my way across. So take the derivative of this with respect to y. Now what are you going to get? With respect to y. X squared plus partial of g with respect to y. Yeah, that's not a prime because that's a function of 2 variables. This is absolutely correct. Whatever my call it your grandfather function, if you will, whatever my f is, the partial of f with respect to y is exactly equal to this. I don't know what that is, but I also know that it's equal to this. So I'm going to set these two equal. You with me? Now we got this. So the partial of g with respect to y is negative 4z squared. Anything is possible on the right-hand side except I cannot have any x's. We did all the x's. There can't be future x's down the road or they would have shown up. Okay, now we need to find g. So what is g of yz? It's the integral of this with respect to what variable? Y. Because, sorry, letter y. Yeah, because this was the derivative with respect to y. I got to integrate with respect to y. Does that look confusing at first glance? That I have different letters there? Yeah, that looks totally weird. In Calc 1 and 2 I couldn't do that, but remember, we're starting with x, y, and z being independent variables. In Calc 1 and 2, these have to be the same variable. In Calc 3, they're rarely the same variable. And they never have to be the same variable. I'm integrating with respect to y. This is an independent variable. Oh, so in terms of y, I treat this like a constant. So therefore, what is this?
Negative 4z squared y.
Plus constant, right? Plus, I like using h2. Plus something that potentially could be purely z-ish. Because at this point, That's either gonna be a constant or it's gonna be a function of z. Because right now, if I took a derivative of this with respect to x, it would have been 0. With respect to y, it would have been 0. But if there's something that's purely z, it would not have shown up in either one of those derivatives. That's why we allow for the possibility. In my first example, it ended up being a plus c, didn't it? But in this case, it's actually not going to be. Now, let's go backwards, retrace our steps. So therefore, on my running total, what is f of x, y, z now? It's x squared y minus 4y z squared plus h of z. I'm resetting it. Why am I resetting it? Because I need to take the partial of this entire thing in order to set it equal. You don't take partials of just the g. A lot of folks make the mistake and only take the derivative of this. That won't work. If you only take the derivative of this, it's not going to match your last thing generally. Not generally. Not yet. So I got to take, this is my f. I still don't know what this is, but this is what f looks like. So now what we're going to do is take the partial of this with respect to z. Nothing there. What do I have here?
8yz.
Negative 8yz plus, can I say h prime?
Yeah.
Can I do that? Yeah, because it's a function of one variable. You just can't use prime when it's a function of two, because it's ambiguous. And what do I do with that? It must equal this. Okay? So now what have I got? I've got that h prime of z is equal to the sine function. So what's h of z? Will that be the integral of sine z dz? Now, you could do that in your head, I know, but I'm reminding myself because these didn't necessarily match, right? So I want to make sure I'm integrating with respect to the right variable. If I used any other letter, this might not work so well. Now what is this? Can I say plus c now? Yeah, there's nothing left. So now I can say plus c. Can we now state the potential function? Yes, we can. So f of x, y, z, after all of this, where is it? It's in there somewhere. X squared y minus 4yz squared minus the cosine of z plus c. And you see that every step we did was necessary. We didn't skip any steps. But if I don't do the little things, this wouldn't have worked, would it? So the algorithm is, and the easiest way, I always just do this one dx. When I integrate that, instead of putting a plus c like you're used to, you say, no, I may have another variable that's not x. So in 2 dimensions, it wasn't as obvious, but in 3, it's a little more obvious going, oh, I integrated with respect to x, so I got every term that has an x in it. But what if they're terms, they're still terms, but they don't have x's? They would have gone away on that first partial derivative, so that's where we account for them here. There can't be an x here, but there can be both a y and a z. Now, could this still be a plus c? Sure. It could be, but if I say plus c, then I won't be able to finish the problem. So I say plus whatever variables are still left, and that's why here, that was the only variable left. And now we got to the end of the problem. So now, the question came up earlier, how do I know that I'm right? How did all of this work? Could I have messed something up? Could it, especially with me, you know I could mess something up. Could you make a plus or minus error at this point? Ooh. How do I check this? How do you always check integration? Take the gradient of this. You get this back again. That's it. That's your check. Because you could have a flawless understanding of this, and if you do 100 problems and you get 95 of them right, I'd say you're doing great. But are you still going to make mistakes 5% of the time? Probably. So how do you know? You checked it by differentiation. You took the gradient and said, do I get back all those same terms? Oops, I lost a sign. Oops, I lost a coefficient. Oops, I lost an exponent. Yeah, it's going to happen. But the check is actually not very hard. And it would be really wise to do the check. Okay? Because to do all of this work and not ensure that you got the right answer. So now, where does this problem come up in the question? Here's where it comes up. Let me erase this. Let's pick something simple here. Hold on. I asked you a question that was very much like this. One of the first work problems we did where I said from this point to this point, and then we figured out that was t equal 1 and t equal 2. Remember that? So I actually asked you from point to point. I'm saying calculate the work done from point to point, but what's missing? I didn't give you a path. Ooh. What if this were not conservative? Then there's an infinite number of answers, and this is a really terrible question. But if this is conservative, then we say if this is conservative, then this is independent of path. I'm going to get a numerical answer that does not rely on the path I took to get there. So in a problem like this, usually if you're asked this question, it's like wink, wink, nudge, nudge. Yeah, it's conservative, otherwise it's not a very good question. So usually the instruction would be something like this, you know, show that it's conservative, then do your dirty work. So you would say, but you don't see a force vector in this statement. Yesterday you did not see a force vector in the statement. Today do you see the force vector? Yeah, I showed you how, and you go, oh my God, it's actually that simple. That's M, that's N, that's P. Yes, but I had to show you today. I derived that today. So I have, there's the question, so you go back to here and say, let me do my dirty work on this. Okay, good. My vector, my force vector is conservative, therefore this integral is path independent, so all I need to do is find the potential function, and that was the series of integrations we did. Was that a short problem? No. But if I had given you a path in 3D that you would have had to parameterize, you think that's a short problem? Oh my goodness, that is so much longer, and those integrations may be so much more difficult, because now I'm making everything a function of t, and what do you do with this cosine of z? Z is now a function of t. So now you have a cosine of a function of something, you have to integrate it without the benefit maybe of a chain rule factor. In other words, yeah, that problem's way worse. Let's just leave it like that. Question?
Can you extend this process to like an n-dimensional vector?
Yes, but we don't really have application for that. But yes, you could do this. I love those kinds of questions. Could I do this in a higher dimension? Yes. But what is the point of this? This is extremely applied. This is a pure physics application problem to be able to calculate work. So if I'm in a higher dimension, then I'd have to define things a little bit differently. And it's like, okay, then what is my force representing in the fourth dimension or fifth dimension? The mathematics is the same. I just don't know that I could give it any meaning from an application standpoint. Okay, I told you guys about the book that a few summers ago I read, the E equals mc squared. You know, again, I've slowed down my aging because I run really fast. But the fact is that the book is based on fourth dimensional non-Euclidean geometry, which I think is really funny because you're explaining the 3D world using fourth dimension. Well, we live in 3D. Do we have any difficulty understanding two dimensions? No. I mean, you're watching TV, that's two-dimensional. You're looking at a picture, that's two-dimensional. You're looking at the board, that's two-dimensional. When we do projections, those are two-dimensional. But to try to work backwards and think in 4D and give that application is difficult. Us being the three-dimensional projection of something in 4D, that's mind-boggling, but that's how we can get here. We can always explain it that way. That's kind of some of the stuff they do. And that's not easy to understand. There is application, but that's about the only time I've ever seen a higher dimension applied. So I would probably not worry about it. It's interesting. Now, having said that, how many will be taking linear algebra in the fall, probably? Linear algebra, the entire point of the course is multidimensional. You're not bound to any particular dimension, so everything's n-dimensional. All the examples we do in 2 and 3 so we can keep the level of algebra under control. But then understanding once I establish the rules, it's the same in all dimensions that are higher, and then you do stuff in 4 dimensions every now and then. That's not really a big deal. If I give you a vector with 4 components, does that all of a sudden make the problem hard? No, you might not be able to give it physical application, but doing the mathematics of it is no big deal. So linear algebra is multidimensional. We say everything's n-dimensional, and we do not limit ourselves. Not at all. What is the only thing where dimension is determined and limited in? The only thing we've dealt with. Cross product. Yeah, and cross product is not even a thing in linear. We introduce it, we bring it up, we talk about it for, I don't know, like a minute and a half, and then we move on. No, dot product is the only thing that you actually use. And in mathematics, as you go on, dot product is used a lot. Cross product is never used in a mathematical context ever, but it is used for physics because of its physical application and its sheer importance. So I want you to be able to do this problem from beginning to end in general. You guys want to do another one? Let's do a 2-dimensional one, because I want you guys to do it now. All right. Too much writing. Oops. Actually, I'm gonna leave this like this for a moment. I'm gonna just say, I'm gonna say from point A to point B for now. Yeah. Because the numerical answer at the end, you learned how to integrate, you got really good at integration, then you learned definite integrals. Was that a whole nother big, huge thing, or is that just a tiny, tiny, tiny add-on? You took your answer and then you evaluated it at a number. That's not calculus anymore. I did all the work to find my function. Oh, evaluated at 3. You know, minus evaluated at 2 or something like that. The definite integral is just one more step that's the lowest level of math, because all you're doing is plug and check, right? You're just calculating a number. I would like to know if that's a conservative vector, and if it is, can you tell me the potential function? And then my final answer, if it is, would be, you know, f of this point minus f of this point. That's all you do at the end of the problem. So those points are irrelevant. It's just I plug them in at the very end. I need to know, is it conservative? And if it is, what's my potential function? But this is a vector in R2. How do I know that? Could this be 3-dimensional? Technically, it could be 3-dimensional because it could be plus 0 dz. Ooh. But the fact that there are no z's means my force, even though you could say it's in 3 dimensions, my force would be entirely on the xy plane. And therefore, my movement has to be entirely on the xy plane because there is no z component. So this, yeah, this is 2-dimensional. It's not a trick question. All right, so this is M, this is N. What are you comparing here? So let's do it. So what is my?
6x squared y.
6x squared y. What is nx?
6x squared y.
Check. What is the next thing you would say in words?
The force is conservative.
Your force is conservative. Good. So the integral is, the force is conservative, so the integral is path independent. They go hand in hand. If I'm just giving you a vector, there's no integral, so you don't need to say path independent. The integral is path independent. Forces aren't path independent, they're just forces. There is no path, it's a force. The integral involves a path. Right? I'm saying point A to point B, and the path doesn't matter if it's conservative. So this is conservative, so now I want you all to find the f. I'll give you a couple minutes. On your own, see if you can figure out how to do the integration. This is not complicated. I'm using relatively simple functions. Okay? Do you already have the answer? But you do. Oh, I was talking. There is an interesting question that you're going to deal with in Math 255. Let's suppose this was not conservative. Okay. What if I told you there's a really good chance if you multiplied your vector or both components of your vector by the right thing, it would make it conservative? In other words, let's just pretend for a moment this was not conservative. But if I multiplied both m and n by, x squared, now it would be conservative. But just suppose, do you think that's a stretch? That I could take something, or here's another way of thinking about it, as we're working on that. Let's suppose, in my head, here's what I'm thinking. All right, let me make this, I'm gonna make it x to the 4th y squared minus y to the 6th. Okay, so now my f is 4x cubed y squared, and then what? 2x to the 4th y minus 6x y to the 5th. Okay, great. Okay? So just for the heck of it, I'm going to take out a y squared. I have a new force vector. Let's call it 4x cubed. Oh, I'm sorry, I'll take out a y. Sorry, I'll take out a y. Then it would be 2x to the 4th minus 6y to the 4th. Everybody see what I did? I just pulled a y out of each of these terms. If I take the partial with respect to y, I'll get 8x cubed. If I take the partial with respect to x, I'll get 8x cubed. I know this is conservative. This is not conservative anymore. I removed that y. This is a dead end. Do you agree? Can't go anywhere. Partial with respect to y is 4x cubed. The partial with respect to x is 8x cubed. They're not equal. This one I can't do anything with. I can't integrate. Darn. Why did you have to pull out that y? Well, you didn't know. I'm handing you this vector, but you know how I got it. So what if there was a way I showed you to figure out that it needs a multiple of y, and you multiply it by y, and now you have this? Wouldn't that be cool? Turns out there is such a thing. And it turns out to be one of the most important things you'll ever learn in a calculus-related class. The vectors that are not conservative, you may be able to make conservative with the right multiplier. Cool. Doesn't that sound cool? Now, it doesn't work for everything, but a lot of times it does work. A lot of the time, not all the time. And it's a technique you're going to learn fairly early on in a DiffEq class. And so there may be another way to attack something. Then after I figured out what to multiply it by, it may be compensated later on. I may have to pull it out or something. But it's kind of a cool concept that you might be able to fix it. So, does anyone have an answer?
X cubed y squared minus 3x squared plus 8/3 y cubed plus c.
I got
I
it.
got 6y cubed.
So say what the next term was? It's not that. So what did you get?
Should be 6, yeah.
Minus 6.
3x squared plus
Minus 3x squared
Plus 6y cubed.
6y cubed.
plus 6y cubed. Does everybody else get that? And do you all get that? Now, hopefully that was painless. Okay, so what did you do? You integrated this guy, and when I integrated this guy, I got these two pieces back, didn't I? But I did not get this one. So then you put a plus g of y. Then when you take the partials with respect to y, that's how you can figure out what this piece is. If I had put simply plus c, then this would not be there, would it? And so that's why we don't just automatically put a plus C. We put plus whatever variables are remaining. Does it mean there's going to be one? No, but it means there might be one. And then I'm covered. Okay, question? Everybody cool? All right, tomorrow, big day, big day. Okay, important day. I've already got a lecture from last fall, put onto Canvas. Has anyone actually taken a glance at it? I don't need you to, you might not be here, right? So that would be wise. I'm going to record, so I don't know that, I think what I did was I put the date on that one. So I'll go ahead and put both of them on here. I don't think you're gonna see much difference. I think what we did though, and I might need help tomorrow, Makai, is I start over there, so we might have to shift the camera. It's one of these things where I'm gonna use up stuff over there so I can do stuff over here and then refer back to stuff over there, because then we're gonna finish and maybe even end up over here. It's not that it's difficult, there's just so many pieces to the puzzle, and I hate erasing. As we're developing something, I may refer to now, remember that thing we did over there? So I will leave stuff up for a really long time so that you can see the development, and then we're gonna get this humongous thing going here. Humongous thing going. It's a biggie, but it's also the last material that will be on the next exam, okay? So it's also, another reason. Let's go ahead and stop.